Okay, so we're going to have a copper box of mass 3 kgs sitting on a steel bench what force is required to move the box along the bench. A, with no lubrication, and that formula over there tells us that in that case the coefficient of friction is, just reading these off the engineering toolbox, call it 0.5, looks about right. And with lubrication, so there's some oil or something on the bench, and that gives it down to in the order of 0.2. So those numbers I've just read off the engineering toolbox website. Okay, so whenever you're doing one of these questions, it's usually a good idea just to draw a little picture. When it's flat, it's kind of obvious, but if it's going to be on a slope or there's any forces acting on slopes, it's much easier if you just have a picture in mind. So you've got your steel box sitting on your bench. You're going to apply a push on it. And that's what we're trying to find out. We're trying to find out how big that push force is. Which way is friction going to act on this diagram? The other way, so back the other way. So you can either, it doesn't matter, you can draw it here or here, it makes very little difference. So let's put friction going back this way. Okay, what other force or forces are acting on this box? Gravity? Yeah, so let's have and how much is gravity in this case? 3 times 9.81. Yep, 29.4 newtons. Yep, awesome. Any other force you want me to draw on this thing? Is that going to be an equilibrium like that? No, what's the problem? What's going to happen to that box and if we let those forces act on it? It's going to, what was that? Yeah, it's going to go down, isn't it? With that at the moment, it's going to go down. So we need an upward force. Okay? So this upward force is the normal force. So it's the bench pushing back on the box. And the size of that force is going to be 29.4. Okay, because our box isn't going up or down, it's just going along. So whatever's pushing it down, gravity, has got to be equated by whatever's keeping it up, which is the reaction force of the bench. Normal. Yes. Well, because you're going to need them when you come to use your formula, which says that, remember the formula I said is that the coefficient of friction is FF divided by N. So you need to work out what N is to be able to use in that formula. And in this case, because everything's flat, it's easy, because whatever the weight is going to be N. So on a flat surface with all your forces acting horizontally, you can just replace N with the weight. But that's only that real simple case. We're trying to find the force of friction. The force of friction is equal to U times N, which is without lubrication 0.5 times 29.4, which is half of 29.4, can be 14.7 maybe. Yeah. So the force of friction is going to be 14.7 newtons. So to keep the box moving, you have to overcome that. So the net force is 0. So that's going to be the same as P. So P is, in this case, the same as the force of friction. So overall, we have no forces acting. So if the box starts moving, it'll keep moving. And for part B, it's exactly the same, except now we're going to use 0.2 rather than 0.5 because we're doing it with lubrication. So what have we got there? We've got about just under 6, maybe 5.9 or something. Someone would better let me know if I got that wrong. 25, it's 29.5. So it'd be 5.8 something that rounds up to 5.9. Yep, so it rounds up to 5.9. Brilliant. Okay, so on the really simple level questions, and honestly, quite a few of the old exam questions on this topic are basically this. Something just moving along the flat, being pushed along the flat, and it asks you what force is required to keep them moving. And that's all you have to do. The other way the question sometimes goes is it gives you the force and the weight and asks you to calculate the coefficient of friction. So you just don't even have to rearrange, you just put the numbers in and get the coefficient of friction.